Hello, students. I just really quickly wanted to finish up a discussion we had in class, but ran out of time to finish. So when we were on problem 5, we looked at the circumstances under which the component of the projection of B onto A is the same as the component of the projection of A onto B. And I think we were thoroughly convinced doing this kind of algebraic manipulation that really the components are the same. That requires that the length of the vectors be the same. And then for the projections, when is the projection vectors themselves? When are the projection vectors themselves equal? Like when is B projected onto A, that vector equal to the vector A projected onto B? And some algebraic manipulation got us to this point, that A over the length of A squared has to equal B over the length of B squared. And there was an interesting discussion about where Kaylin was convincing us that actually this means that A has to equal B. And I want to just wrap this up because this is good to think about. And so her argument was that if you separate this into, I guess her argument started first with noticing that this here means that A is a scalar multiple of B, and so A is parallel to B. Because A equals, if you just multiply through, we've got A equals A squared over B, length of B squared, times vector B. And this is a scalar. And we know that for two vectors to be equal, or to be parallel, one has to be a scalar multiple of the other. So, okay. So we know they have to be parallel. And then she said, okay, well, let's have A divided by the length of A times 1 over the length of A. That's going to equal B divided by the length of B divided by 1 over the length of B. And then the claim was, well, these two guys are parallel from over here, but then they're also unit vectors. And so then the idea was, well, okay, they're parallel unit vectors. If they point in opposite directions, so if A is minus B, then we'd have one side being the negative of the other. And so, and that doesn't work. And so we have to say, well, then not only are they parallel unit vectors, but must also point in the same direction. And so these two unit vectors are parallel and point in the same direction. That means they're the same vector. And so then the argument was that means that 1 over the length of A must equal the 1 over the length of B. But that just means the length of A equals the length of B, which means that not only must A and B be parallel, but they have to have the same length. So then the claim is, since A and B are parallel and same length, I guess, and point in the same direction, that means that A has to equal B. So that's an interesting way to do this problem. And I'll say it's slightly different than the way I thought about it, but I think, it's good. So I'll maybe in red say the way I was thinking about it just to get another perspective. But, there are tons of ways to skin a cat. So here's another way to do it. Again, starting from here, I was kind of thinking geometrically and thinking, well, if the projection vectors are the same, then the components also have to be the same. So if the projection vectors are the same, then components are too. And then the thought is, well, if the components are the same, then length of A has to equal length of B, because we just said, all right, the components are the same. But that means that length of A squared has to equal length of B squared, which would then imply that just A equals B. That implies A equals B. So two ways to get to that conclusion, but I would say it's, in either case, it's not obvious just from here that that's actually where you get. So it takes a little bit. So, okay, that's the first thing I wanted to talk about. And then we never quite got to number 7. And so I want to say a couple things. I guess I want to show how number 7 goes. And the first thing I want to say is that for number 7, this is geometrically should, if we draw the picture, we should find this very believable, that the vector of B minus the projection of B onto A is orthogonal to A. So if we draw a vector A and maybe draw a vector B here, and we drop a perpendicular down, this vector here, that's the projection of B onto A. And now, geometrically, what is B minus that projection? Well, I claim it's that this right here is B minus the projection onto A of B. And if you didn't believe me, add these vectors. Projection of B onto A plus B minus projection of B onto A. Add them together, you just get B. And so this is really like the perpendicular component of B. And so they really should be orthogonal. But I would say you should be comfortable with an algebraic way to prove this. And the algebraic way to prove this involves the dot product. And so you wanted to show that two vectors are orthogonal, you got to show that their dot product is 0. So you want to show that B minus the projection of B onto A dotted with A equals 0. So let's do some calculating. From our properties of dot product, if we do B minus the projection dotted with A, using properties of the dot product, we can distribute A like the dot product through. That's equal to B dotted with A minus the projection B onto A dotted with A. And then let's remember, what is the projection? So B dotted with A minus projection of B onto A is A dot B over the length of A squared. All of that's scalar, times A. So that's this. And then we're dotting that with A. All right, now remember, A dot A, that's equal to the length of A squared. So that's equal to B dot A minus A dot B over A squared times, whoops, maybe I won't write a dot there, just times length of A squared. These cancel. B dot A equals A dot B, so that equals 0 as desired. Okay, sorry I didn't get to this in class. Great class today, everybody. I'll see you on Thursday.